Yeah, sorry for the delay. I had some departmental activities. Yes, sir. Pardon? Yes, yes, absolutely. Yeah, thank you, sir. So I'm presenting Sharad Institute of Technology, College of Engineering, one of the autonomous institute with the earliest track record of having autonomy. So I also extend my thanks to Dr. Bapuji Solanki Institute of Technology, Kolhapur, for giving me an opportunity to be a resource person in this hydrogen energy and fuel cell, which is scheduled in the 1st September to 6th September. So again, thank the electrical department for taking this initiative uh, and giving me a chance. I think it was just happened in a very short period of time. So whatever is possible, I share my knowledge. So if anything is missing, I just ask apology in the beginning itself. Uh, Sir, hope the slides are visible.
Yes, sir. Yes, sir.
Yeah. So now, as the FDP title is linked to the hydrogen energy and fuel cell. So now, actually, what is this hydrogen energy and how it can be converted into the fuel cell? And whatever the topic given for me is to again address the challenges of the session, and in the sense hydrogen energy and also the infrastructure development. So whatever till today we have the infrastructure development and what is going to be the future challenges. So these also points I'll address. So first we'll go with some basics. During the slides only we can identify what is the present infrastructure developed all over the world, as well as where we are lacking or where the challenges are there to be addressed in all the right from its R&D to the on the field how we can execute that one. So we'll start with some basics. So once a scientist called Jules Verne, in the year 1874, he said that what are the new coal? So as we all know, there are again renewable, non-renewable sources of energy. So so he predicted that in future water can be a new replacement for the coal for energy generation. In the similar way, a scientist called as Dieter, he also put his views in the hydrogen that is a better oil in terms of energy. So, which future role for hydrogen as an energy is possible in the carrier? So, this is what the perspection in the earlier days, what the some of the scientists with their knowledge and with their a lot of R&D works, they have given these statements. So now, as I'm from the material science background, so anything we start the discussion first. If any material is given for a material science engineer, so first we always start with the phase diagram. So now at the present discussion is the hydrogen. So now if you can see in the phase diagram, this is a single phase diagram, means only one element is there. Again we have dual elements phase diagram also. So now this is a single element phase diagram. So as we are aware that whatever the element is there, it can be present in multiple forms. Any element can be present in multiple forms, so with some terms and condition or whatever the conditions, atmospheric conditions. So now you can see here some lines, dotted lines and the straight lines. So you can see that some namings also. On the extreme left side you can see that is solid, and the next to that is liquid, and in the bottom we have the gaseous state. So this phase diagram refers to the temperature versus pressure. Temperature in degrees Celsius, pressure in the bar. Now we have a triple point wherein it is named as a critical point. So the conditions for this triple point to exist is 13 bar and the minus 240 degrees Celsius. So now we can imagine how it is possible to store any material in a so much of minus degrees Celsius. That is again it's a wonder of engineering and technology that we call as a cryogenic temperatures. So now we can see whatever the level of bars and the temperature. For example, near to the 100 bars and the whatever the 260 minus 260 degrees Celsius, the hydrogen can be, we can store in the form of the solid. And the similar way 100 bars and 250 to 260 in that range we can store hydrogen in the liquid form, and nearly about 10 bar pressure and greater than, so the less than 250 minus 250 degrees Celsius we can store the hydrogen in the form of gaseous. And again we have the supercritical fluid that is above the critical point. So whatever again one more phase what we can call that is a supercritical fluid. As the name itself says, it is quite difficult to achieve that phase, that is which is above the critical point. So that critical point is nothing but at the, again I have told, 13 bar and the minus 240 degree Celsius. So with this you might have got the fair amount of idea. So at what temperature and what pressure if we play with the hydrogen, how we can store it. So this slide you can correlate whenever the storage capacity of the hydrogen slide comes. So at what temperature, at what ambient temperatures, how we can store the hydrogen. And again in the storage also we have a lot of challenges. So to link that, my initial explanation started with this phase diagram of hydrogen. So now, as we know, we have n number of materials for the as a fuel, right from petrol, diesel, biodiesel, ethanol, propane, methane, and hydrogen. So now, one thing everyone is aware that now only the purest of petrol and diesel, that era has been finished. Now if you see all these two fuels are blended with the methane and the methane elements. If you see as per the central government norms, we get the biodiesels. That is nothing but the blending petrol or the diesel with the methane and the methane related groups. So that is again depends upon the 10%. Still in India we could achieve the blending up to 10% only. So that is why that rules were made. I'll just give some basic information. So as you all are aware that post-COVID, the central government imposed BS6 vehicles to be launched and they should come into the market. So earlier to BS6 we had BS4 vehicles. So what is the actual difference between the BS4 and BS6? There was a gap of BS5. So first strategy what the central government took is to reduce the emissions due to the whatever the petrol and diesel we are burning into the engines. So if you can see one example I give, if anybody is having a BS6 two-wheeler, So you can just see what is the changes in the technology. The changes in the technology is your carburetor is being replaced by the fuel injector, whether it is petrol also. So whatever this fuel injector we used to get only in the diesel vehicles, that has been replaced in the petrol, that is carburetor is replaced with the fuel injector. So again you can see in the silencer whatever the noise is controlled, all the vehicles are exhaust phenomena is very silent, so you will never get any irritated kind of the noise because of the silencer, right? So again the silencer is one of the technology wherein the sound and the impurities are being absorbed and the environment is getting quite pured whatever the exhaust air, right? That again depends upon the person to person how he or she maintain the vehicle. So that is one point in discussing how the petrol and diesels are being replaced by the biodiesel. That is the one era. And the future era, whatever the almost all the countries in the world as well as India are working on the hydrogen. Uh-huh. Hello. Yeah, sorry for the interruption. So now the world as well as the India is working on the hydrogen technology. So that is what is the future. So again in that how to generate the hydrogen from the existing whatever the materials we have. So that is again we will discuss. So now this is slide is relating to the ignition ranges of the
Let
fuels.
him attend. He's not disturbing. No?
So now here you can find in the labelings, that is gray color is mixture to lean, yellow is ignition range, dark gray is mixture to rich. So whatever the percentage is on one side of the graph, 20%, 40%, 60, 80 and 100. So in this one we can identify that whatever the ignition ranges of the our existing fuels what we have. So now coming to the share of primary energy carriers in the global hydrogen production. So here you can see in the pie chart, the gas is contributing to 68%, oil is contributing to 16%, and the coal is contributing to 11%. Electricity is contributing to 5%. So these are the what are the primary energies which is required to generate the hydrogen production. So hydrogen production, it is by default we cannot generate, we have to go into the multiple ways wherein we have to use the gas for burning, so that it helps in converting the whatever the water into the hydrogen and the oxygen molecules. So again burning the oil it may be, or burning the coal it may be, or we may use the electricity as well as. So this is the chart which represents primary energy used in the generation of hydrogen production. Now coming to the what are the ways or the process for producing the hydrogen energy. So as we know, there are three types. One is gray hydrogen, second one is blue hydrogen, and the last one is a green hydrogen. So in between the partition, you can see the years. So before 2020, You can see the worldwide it was concentrated on the gray hydrogen. After 2020, now we are in the era of generating the hydrogen by blue hydrogen. And after this, or some of the countries have started their trials, that is with the green hydrogen. So full-fledged may take after 2030. So now what is exactly this gray hydrogen, blue hydrogen and green hydrogen? So if you can see in the gray hydrogen, whatever the primary energies we are using, that is coal, natural gas and the biomethane. So these after burning either of these three, so whatever it will undergo the phenomena called as reforming. So after that, again it is liberating some lot of amount of carbon dioxide. That is footprint of carbon dioxide is very much high with the gray hydrogen. So again, it is an bad impact for the environment. Even though we are producing the hydrogen, the way it is produced is again liberating the carbon dioxide into the environment that causes the greenhouse gas effect. So again, that is nothing but the whatever the coal, natural gas, and biomethane we are burning. Because of that, it is liberating the carbon dioxide. So we cannot eliminate that one. So then next, the future started with the blue hydrogen. Here, whatever the primary sources of energy are natural gas, biomethane. So it will undergo the reforming process, or it can undergo the gasification process also. These are the two process which will undergo under the blue hydrogen. So your capture of carbon dioxide is quite less than that of the gray hydrogen. So whatever the emission is quite less than the gray hydrogen. So that is what the blue hydrogen. So now the future will be the green hydrogen. So why that it is terminology as green hydrogen? Here it is there is no emission of carbon dioxide, only it is the emission of oxygen. So now this here the primary source of energy is water. We are using the water, it will undergo the electrolysis process, and whatever the hydrogen and the oxygen molecules can split up to liberate the oxygen, and whatever the hydrogen is separated out, that can be stored in some pressurized condition as well as some ambient conditions or the cryogenic conditions. So here, right from the gray hydrogen, maximum carbon dioxide deposition is there. Blue hydrogen is quite less than the gray hydrogen. So in green hydrogen, there is total elimination of carbon dioxide into the environment. So now, what are the uses of these primary uses of the generated hydrogen? So that it can be used in the transportation. Nowadays, you can find the in India the very first hydrogen powered vehicle. Now, if you see, it was inaugurated. That is, a Toyota company launched the one of its kind hydrogen powered vehicle that launched by Toyota. So you might have seen some press conference or the meetings held by our transportation ministry, Nitin Gadkari sir. So he himself is using one of its model for his personal use, right? So again, whatever the hydrogen generated, that can be used in the chemical industries also. Lot of chemical industries, while their chemical operations, they require the hydrogen. So that you might have seen the hydrogen stored in a tank, right? So that is also required in some of the chemical industries. So again, energy and storage. So now the hydrogen can be stored in the form of energy. So that is again nothing but the fuel cells. Then next one, liquefaction and export. So again, this is the biggest challenge, how to transport the hydrogen gas to the other countries. That is why the liquefaction is required. So storing the hydrogen in an gaseous form is next to like is very quite dangerous. So as you have seen, exporting in a heavy quantity, that goes into the sea routes. So sea route is nothing but it is very rich in salt content. So anything is stored in high pressure and anything is stored in cryogenic temperature and high temperatures. It is very dangerous to carry such things in through the ships or the sea routes. So that is again one of the biggest challenge how to store, that we will discuss again in the future slides. So now coming to the processes for producing the hydrogen, as we have discussed in the earlier slide, I have that the same thing I try to elaborate here. The first is you can see the primary energies, then secondary energy, conversion, and then intermediate or intermediary product, and the final energy carrier. Now solar wind is used as directly as an electricity that undergoes the electrolysis. So now this is a example for the green energy, or producing the hydrogen through green energy. Means here we are using the solar or the wind as an primary sources. So from that, whatever the electricity is generated, that we are using as a secondary energy to for the process called as electrolysis, to split the water molecules into hydrogen and oxygen. So the final output here, we don't have any intermediate product. Then we directly get, after the electrolysis, hydrogen and the separated out oxygen molecules. Then again next we have algae from sunlight, algae from the sunlight. So it will undergo the biochemical conversion, and again it will give the intermediate component that is called as syngas. So by the whatever the syngas, we can again split up, or it will go the process and it will give us the final output as hydrogen. So in the similar way, biomass is there, so it will undergo the biochemical conversion. So biomass, in the sense, it may be biomethane, biogas, ethanol, and the vegetable oils. So all these are considered under the biomass. So again, it is undergoing the biochemical conversion. Intermediate component is again the syngas, and finally we'll get the hydrogen as an end product. So then again we have natural gas, oil, and the coal, wherein it will undergo the thermochemical conversions. So that is SMR. So that is steam methane reforming, or partial oxidation, or autothermal reforming. So again, the all these three processes will give the byproduct called as a syngas, and finally we'll get the hydrogen. So these are the three processes which will give the final hydrogen as an end product. So now we'll be more focusing onto the electrolysis process, because the world is moving towards the green energy, or the generation of hydrogen through the green sources. So that is earlier slide also we have discussed. One of the method is electrolysis process. So as we have studied in our in the basic fundamentals, that is in your chemistry or any higher chemistry classes. So electrolysis process having a bath, that is here now nothing but the bath is water, and we have the two electrodes, anode and the cathode, which are dipped into the solution, and the current supply is given, right? So once the bath is processed for the electrolysis, it will separate out the oxygen molecules, and it will separate out the hydrogen molecules. So now whatever the separated out oxygen and hydrogen molecules, we can utilize it. So oxygen is readily, we can liberate it, divert it to the atmosphere, and whatever the liberated hydrogen is there, so it is we can be stored in the multiple ways. Now coming to the sector coupling, that is power to X pathways. So again here again the combinations are shown here. So how the final hydrogen is stored. That is one. Power to gas, so that is undergoing the methanation, so which will again liberate the carbon dioxide, correct? And power to liquidus, so again the synthesis with the help of petrol, diesel and the jet fuel, again it is liberating the carbon dioxide. So whereas in the green we have seen use of sunlight and the windmills, that generated electricity we are using to carry out the electrolysis, that will split your oxygen that can be readily diverted to the atmosphere, and whatever the hydrogen is there, that is stored in the storage devices. So again that stored whatever the hydrogen is there, that we can pressurize with the pressure, so whatever the required pressure, and we can store in the ambient climatic conditions, and that can be supplied to your grids. Means in the, as we have the petrol pumps in our regions, in future we will get the hydrogen fueling centers also. So as we have nowadays we have the battery charging stations also. In a similar way, in future we will also get the hydrogen refilling centers. So now coming to the energy input for hydrogen supply. So how much energy input has to be given for the generation of hydrogen? So that is, on one side we have the megajoule per megajoule of generation of hydrogen, right? So on the x-axis we have the multiple combinations, that is EU gas mix reforming. So wherein you can see the labels. So renewable we have, nuclear we have, the and the fossil. So in the first one, more of the fossil fuel is being used, and in a small content nuclear, and very few we are using the renewable energy. So then in the next one we have the biogas mix reforming. So then again the fossil fuel has been reduced quite to the earlier one. Nuclear, yes, again the use of renewable energy is also increased. Then coming to the LNG reforming, liquid nitrogen gas. So in that again fossil fuel usage is more, and again nuclear is in some proportion, very less in the renewable energies. Whereas coming to the EU electricity mix electrolysis, here fossil fuel we are using as a primary source, nuclear energy, and to some extent renewable. But when you coming to the renewable electricity electrolysis, that which falls under the green energy generation, here maximum we are using the primary energy from which are procured from the renewable sources, right? So again nuclear is very quite less, and fossil fuel also. In the last one, maximum we are using the renewable source of energy. Then next one, let us understand the greenhouse gas emissions during the generation of hydrogen gas. Right. So on the x-axis we have again the same combinations, that is the materials, and on the y-axis we have how much amount of carbon dioxide is being liberated per megajoule of hydrogen generation. So maximum it is shown up to 250 gram of carbon dioxide liberation per megajoule generation of hydrogen gas. So now we'll go with the multiple combinations. One is the dark blue is the centralized paths, and the light one is decentralized paths. So while generation also, whether it is in the centralized generation or whether it is a decentralized generation. So first one is EU gas mix reforming. The centralized gas generation, that is hydrogen gas generation, amount of carbon dioxide liberated is quite less. It is near about plus crossing the 100 gram of carbon dioxide per megajoule of hydrogen generation. So if you consider the decentralized paths, so it is quite more than the your earlier one, centralized. So it is also crossing somewhere around 110 or 115, you can assume it to be. So now then second one, with the use of biogas mix reforming. Again, you can see it is drastically reduced from 100 to near about 60 in both the centralized and decentralized, almost around 60. Why? Because we are using the biogas or the biomaterials, right? So because of which the or the liberation of carbon dioxide is quite reduced from nearly 110 to your 60, we can consider. So then again, LNG reforming, here also it is quite similar to your EU gas mix reforming. So the percentage, if you see, or the amount of carbon dioxide liberation, it is nearly some 110. So similar to your EU gas mix reforming. Again, in the decentralized path also, it is almost reaching near about 125 to 130. Right. So now next one is EU electricity mix electrolysis. So here you can see it has been tremendously shoot up for centralized as well as decentralized paths. It is almost crossing 225 grams of carbon dioxide liberation per megajoule of hydrogen generation. So in both the categories, centralized nearly about you can consider 225, the 230. So in the last one is the renewable electricity electrolysis, wherein the carbon footprint is very less. So that is, you can find that is almost some 5 to 10% of 5 to 10 grams of carbon dioxide liberation per megajoule generation of hydrogen. So you can see both centralized as well as decentralized are going in hand, the same, almost in the same grams, the 5 to 10 grams of the carbon dioxide liberated per megajoule generation of hydrogen. So now these statistics are very important if you want to carry out any R&D works in this field. So you should know the background, how we can generate the hydrogen and how it is affecting our environment. So for the greenhouse gas emissions. Then coming to the production cost of the hydrogen. So blue stands for your current, yellow stands for the projected, and whatever the bars are there, that is nothing but your error bars. What is the minimum and the maximum error bars, or you can call it as a standard deviation also. So now again on the y-axis we have 12 euros per kg of hydrogen. I repeat, it is 12 euros. It is given in the euro, not in the rupees. 12 euros per kg of hydrogen. On the other side, again, we have the different methods adopted. First one is a centralized gas reforming. Again, the current one is less than 2, and as well as the projected is also near to 2. There is a slight variation in the both. If you're coming to the decentralized gas reforming, again it is current one is shooting more than 4 euros per kg of hydrogen, whereas projected is estimated to be nearly some 2.5 to 3. With the centralized electrolysis, again the current value is nearly about something 5.8, 5.9, near to 6, and the projected value is nearly about some 4.2 or 4.3 can consider. With the decentralized electrolysis, only one value is projected, that is current value. It is nearly about 7.9, you can consider, not crossing the 8. So projected value is not mapped for the your decentralized electrolysis. Coming to the centralized biomass, again the current value is projected for nearly 3.5 to 3.6, whereas the projected value is less than 2. Again with the decentralized biomass, again the only one value is projected for the your current picture or the current values. So that is almost about hovering about the value of 5 euros per kg of hydrogen. So this is the incurred cost per kg of hydrogen. So now coming to the what are the density of fuels in different forms. So while whatever your pressure. So density varies with the conditions, whatever the ambient conditions, cryogenic conditions, as well as the high temperature conditions. So you can see the three we have mapped. One is in the liquid form or the liquefied gases, the natural gases, and the hydrogen, directly into the hydrogen. So on the y-axis, you can find volumetric energy density megajoule per liter, right? So on the y-axis, you can find the energy, gravimetric energy density in megajoule per kg, right? So as we have already discussed in the phase diagram, the hydrogen can exist in solid, it can exist in liquid, and it can exist in the liquefied gases, and it can also exist directly into the hydrogen. So now with this one, we can see in the liquid form, whatever the biomethanol, biodiesel, and the diesel with syn diesel and the petrol. So all these you can find volumetric energy density is almost for biomethanol it is nearly 20, and for biodiesel and other things it is more than 30. So and coming to the liquefied gases, LNG is nearly 20, and LPG is you can find it nearly about 25. When it comes to the natural gas, that is EU mix, it is 0 on the y-axis, and for CNG at the 200 bar, it is nearly about less than 10. You can consider as around 7 to 8. Then coming to the direct hydrogen storage, again you can see here some combinations are shown. Liquid hydrogen at a temperature of 20.3 Kelvin. So it is nearly about 9 you can consider. And one more cryogenic gas hydrogen, that is at a 700 bar. So its density again decreased. So again cryogenic gas hydrogen at 350 bar, again it is slightly reduced, and hydrogen it is just a 0, right? So now why it is important, so just identify that how the temperature and pressure play a major role in storing the hydrogen gas. So that is what to say in this slide. Now coming to the hydrogen storage methods. The first one you can find, that is compressed gaseous hydrogen, that is in the range of like 350 to and 700 bars. Next one, cryocompressed hydrogen. Then next one we have the liquefied hydrogen. Again we have the slush hydrogen and the metal hydrides, the liquid organic hydrogen carriers, and again we have the sorbonates. So in the form of the, it may be in the form of the your nanotubes or the zeolites or the MOFs. It can be present in the multiple forms. These are the some storage methods. One is four types are falling under the physical, and other three are falling into the material based, right? Now coming to the hydrogen storage density, as we already discussed with the phase diagram as well as in the earlier slides also, how as I discussed, as the temperature and the pressure varies, we can alter the amount of whatever the hydrogen can be stored. So now you can see on the x-axis the ambient or the temperature conditions or the bar conditions, pressure conditions are reflecting. On the y-axis you can find that is gram per liter of whatever the hydrogen storage. Maximum it is mapped to 100 grams per liter. So now first one is we have discussed cryogenic gas hydrogen. that is at the temperature of 15 degrees Celsius and 350 bars. So 15 degrees Celsius is considered to be the ambient temperature, and again the 350 bars. So here we can store up to some crossing 20, that is some we can consider 20 to 25 in the range. We can store the hydrogen. So now if I change the pressure, if I change the pressure from 350 bar to 700 bar, again we can vary the percentage of whatever the hydrogen we can store. So it has doubled up. If you can see, the value has been doubled up from your whatever the 350 bars to the 700 bars. So earlier it was more than 20, nearly about 22, 23, whereas with the 700 bar, just changing the pressure, it has directly shooted to double, that is nearly more than 40 or nearly 41. Okay, so then coming to the cryogenic temperatures. So if you reduce the temperature from 15 degrees Celsius to, that is minus 250 degrees Celsius, which is a cryogenic temperature. So for that we don't require the maximum pressure. With the minimum pressure also we can store the hydrogen. So that is, you can see there is a tremendous increase in the storage capacity. So it is nearly about, you can find out, that is nearly about 70, nearly about 70. So it is again stored in the liquid form, correct? It is stored in the liquid hydrogen form. Then next one more combination we can see here, with the 300 bar pressure and the minus 235 degrees Celsius. Suppose if I increase the bar pressure, that is earlier one we have discussed, with the 1 bar and minus 253 degrees Celsius, it is we can store that is 70 gram per liter, whereas with the 300 bars and minus 235 degrees Celsius, temperature is slightly changed and pressure is 3 times it is increased. Sorry, not 300 times it is increased. 1 bar to 300 bars. So temperature minus 253 to minus 235. So there is not much change in the amount. That is earlier the next is just 80, not a drastic improvement, right? Then again with the 1 bar, again if I decrease the temperature, suppose from minus 53, let us compare 1 bar and minus 253 degrees Celsius and 1 bar with the minus 259 degrees Celsius. The pressure is remains the same, but the temperature is again reduced. Then there is again somewhere around 81 grams per liter of the hydrogen can be stored. So what is the conclusion of this slide? So in the ambient temperature, consider the first 2 bars. The ambient temperature, that is pressure plays a major role in the ambient temperature. That is 15 degrees Celsius. In the both we have 15 degrees Celsius, but the pressure plays a major role. Pressure plays a major role that can directly double up the storage capacity of the hydrogen. Whereas when it comes to the other combinations, that is when the temperature is changed to minus, pressure is decreased. So pressure doesn't play a major role in storing the amount of hydrogen, whereas the temperature plays a major role in the amount of storing the hydrogen. So now coming to the storage density of tank systems. Storage density of tank system. On the x-axis, you can find the material, petrol, FCEV, and BEV. Right. On the y-axis, you can find megajoule per kg. That is a maximum marked up to 35 megajoule. So the petrol takes up to the nearly some 30 to 33 megajoule per kg storage density of the tanks in the any of the system, as we are using our 2-wheelers and the 4-wheelers. So every two-wheeler and the four-wheeler having an capacity, right? 15 liter, 40 liter, 50 liter, right? So that is nothing but the calculation. So how we can store the petrol. The next one, FCEV, again here we can find out it is nearly about some 9 megajoule per kg. So then battery electric vehicles, so it is very less, so nearly 1 or 2 megajoule per kg of the storage can be done. Now coming to the major challenges what we are facing in the storage of hydrogen for transportation, right? So that is you can see again here I have taken the example with the ambient temperature and the cryogenic temperature, how the temperature conditions vary while storing the hydrogen. So in the first container you can see the tube trailers having the cylinders. So in the condition of 200 to 250 bar pressure, nearly we can store nearly about 500 kg of hydrogen. That is nothing but in the ambient temperature. So as we have discussed in the ambient temperature, that is your normal room temperature, we can consider it to be ambient temperature, and pressure should be high. So we have seen the combinations of pressure and the temperature. So how we can change the amount of hydrogen storage, right? So this is I have specifically have chosen. So in the ambient temperature only, if I increase the pressure from 250 bar to 500 bar, almost doubled. And here you can see the amount of hydrogen can also be stored in the double. That is earlier it was 500 kg. Now it has increased to 1000 kg. Again, it is the ambient temperature, that is room temperature, right? So now again the last one, that is cryogenic temperature and the 1 to 4 bar. So as we have already earlier also we have discussed, in the cryogenic temperature, that is nothing but your whatever the minus degree Celsius temperatures, we need not require the high. We need not require the high pressures. Pressure is very minimum, but the temperature matters a lot, right? That is whatever the earlier we have discussed, minus 259, minus 253, minus 235 degrees Celsius, right? So in the cryogenic temperature, pressure should be less, temperature should be in the minus 250 range, right? So with this, what we can conclude is with a combination of high pressure and ambient temperature, very minimum amount of hydrogen can be stored. Again, with the high pressure and the ambient temperature, it is quite higher. And with the cryogenic temperature and the minimum of the minimum pressure bar, it is highest. That is 4000 kg of the hydrogen can be stored in the combination of cryogenic temperature and the 1 to 4 bar with the minimum pressures. So you can just imagine, as I have earlier only discussed, reaching the cryogenic temperature is very dangerous. So as a material expert, we know that reaching any material to its degree Celsius is a very critical job. So likewise, you require the very sophisticated machines. If there is any small leakage in the machines, it will lead to a very dangerous accidents. It is very difficult. So I'll just give an live example. If somebody has visited any of the your sugar plants, you might have seen the boilers which are working in boiling temperatures. If there is a small leakage also, it will lead to a lot of disasters and accidents. Just imagine water which is boiled to 100 or 200 whatever the degree Celsius. So small leakage also will lead to very dangerous situations and accidents. You just imagine storing a hydrogen with the high pressure or the ambient or the whatever the cryogenic minus temperature is very dangerous. So in the similar way, transporting such kind of the hydrogen is also very challenging task. So generating is a challenging task, and the storing it is the second challenging task, and transporting is the biggest challenge. So as I have discussed, whatever this combination is very dangerous to transport through the sea routes, right? As we have the very salvic water, that is water with high content of your salt, that is very dangerous, right? So that is about the hydrogen, how we can transport. So you might have seen most of the we have seen either it is in some tanks, some cylinders, or some containers. What the people are preferring for the transport, that is maximum we are transporting by roadways, right? So now again, coming to the hydrogen pipelines, what the countries are having in multiple countries, right? So if you take the USA, it is having the 2,608 kilometers of hydrogen pipelines. It may be right from the generation plant to the disbursement to the consumers, or it may be to the intermediate, your dealers or whatever the your stations. So it is a maximum connection we can find in the USA. The next one is Belgium, Germany, France, Netherlands, Canada, and total together all other countries is a 258 kilometers. So now we can map the India in the others because we are still in the R&D stage. Because India is not full-fledged working on the hydrogen, we are still in the hydrogen R&D conditions. You might have seen recently we have the Indian government, the railway ministry has launched the green hydrogen locomotive, that is train. So very soon it will be prototype. One prototype will be launched first. Depending upon its loopholes or whatever, again sophisticated multiple we can get the locomotives. So that is in the train. Again, India is also, as I gave an example of whatever the Toyota has launched one of its green hydrogen automotive. So that is they are still the India is in the R&D research and development activities. So that is where we stand for. Now coming to the global usage of hydrogen. In what all the forms the hydrogen is being utilized, highest is the ammonia 55%, refining sectors 25%, other sectors 10%, methanol 10%. So in all these sectors the hydrogen being used, right? Well, in the for the generation of ammonia, highest it is, refining sectors, other sectors, and the methanol sectors is the usage of hydrogen. Now again I have shown the principle of the fuel cell. So now if you coming to the transportation sector, the hydrogen has to be stored in the form of some fuel cell. So whatever the electrical vehicles, the energy is stored in the battery. In the similar way, whatever the hydrogen is there in the stored, we have to be stored in the form of the fuel cell, right? So that is nothing but the here it is shown. The fuel cell is again includes your anode and the cathode for the electrolysis process, which can split up your water molecules into your hydrogen as well as the oxygen, right? That is nothing but the fuel cell. So stacking this fuel cell in the multiple series order, it will give us the very powerful element, that is storage capacity. So that is what the automotive sector is working on. So as we have already earlier we have discussed, storing is a challenge. So for that, one of the solution is fuel cell can be one of the solution for storing the whatever the hydrogen, right? So nowadays you can find the vehicles. So I give the example of electrical vehicles. Energy is stored in the form of the battery. So that is again whenever the vehicle is in the start condition, it is again some recharging kind. Otherwise, it is totally drained. You are putting it for the charging. So in the here, whatever the vehicles should have the fuel cells, multiple fuel cells stacked in a series, so that you have to couple the total amount of energy, right? So that is the principle behind the fuel cell. So now Coming to the stationary applications, so how we can store and use the fuel cell. So as I said, at present we have the we can see in all the areas we have the petrol pumps, right? So that is nowadays it is being replaced to the your whatever the electrical charging stations. So in future you will get you'll also get the refill section for the hydrogen energy, right? So that is one thing is I have shown the fuel cell, that is the nothing but the refilling cell, that is with the natural gas we are getting the heat and the power. So if I use it as an electrical efficiency is up to 45%. So if it is for system efficiency it is up to 95%, right? So how we can use the hydrogen to the different sectors, right? That is one example. So now coming to the some again one more point, that ownership cost of domestic energy, right? We're all we can find again it is on the x-axis you can find the years of service, on the y-axis you can find the euros, right? So here the multiple graphs you can see that the one is air sourced heat pump today, again air sourced heat pump future, and the gas condensing boiler. So with this, so how we can own the cost of domestic energy, right? So I'm not going to detail about this. So now coming to the technology readiness of hydrogen application, that we call as a TRL, technology readiness level, TRL in short, of the hydrogen application. So it is mapped from, or it is given the rating from 1 to 9. 1 is minimum, 9 is highest. So TRL level 1 means it is into the research and development stage. TRL level 9 means full-fledged it is working. I repeat, TRL level 1 means that sector is in the research and development. If the TRL level is mapped with 9, then that sector is fully in the working condition. So you can see the space sector is TRL level is mapped to 9, the industrial trucks 8 to 9, stationary applications 8 to 9, passenger cars 8, buses 7 to 8, light locomotives 7, and scenting locomotives 6 to 7, motorcycles 6 to 7, so lorries and the trucks 6 to 7, aviation 5 to 6, and the shipping 5 to 6. So as I just said, TRL level 1 means it is in the R&D sector, 9 means full-fledged it is being used. So means full-fledged it is being used in the space, industry trucks, and the stationary applications. Again, as I give the example of Toyota, it has launched its hydrogen car, and nowadays they are working on to the buses also. And already locomotive, as I said, India has launched one prototype locomotive. So right, so that is still it is mapped to 7. The rest all are 6 in the range of 6 and maximum in the range of 5 to 6. That is aviation as well as the shipping. So now coming to the fuel cell concepts for passenger cars. So first is the battery electric vehicles with the range extender, and the second we can find a fuel cell dominant system. So here, as we all know, battery powered electric vehicles. So we have the hydrogen tank, fuel cell, converter. Again, the energy is given to battery, and it is interfaced with the converter, and that energy is supplied to the electric motor, and you whatever your axle will get the power, and your both the wheels are drive. So whether it is a two-wheel drive or if it is four-wheel drive, all the wheels are given the power. So that is the difference between a two-wheel drive and a four-wheel drive. So what is the change in the fuel cell dominant system? Your hydrogen tank is there, fuel cell is also there, and here only one converter is replaced, and it is fuel cell is directly connected to the converter, and again it is interlinked with the battery, and whatever the power is coming out it is supplied to the electric motor, and from that the axle and the wheels are getting the power. So this is a concept of how the industries are working to generate the fuel cell technology in their automobiles, right? So don't confuse with the electrical vehicles and the hydrogen powered vehicles. Electrical vehicles, that is you are charging the battery and you are powering the vehicle. So in the hydrogen uh, concept or hydrogen technology vehicles, so your fuel cells are there which are responsible for the electrolysis process. So a hydrogen tank that is again supplied to the fuel cell and the converter and the energy stored in the battery, and then you are powering the electric motor to drive the vehicle. So this is the difference between your electrical vehicles as well as the fuel cell, that is hydrogen dominant systems. So now coming to the fuel cost comparison. So here you can find the hydrogen, petrol, electricity on the x-axis. On the y-axis you can find that is cost in euros per millijoule. So per megajoule, sorry. So cost in euros per megajoule. So now hydrogen you can see. So that is 7 euros per kg, right? So it is again reaching up to maximum 9.5 euros per kg, whereas petrol again it is in the 1.5 euros per liter and 2.5 euros per liter, and whereas electricity it is 20 octane per kilowatt hour and 35 per kilowatt hour, right? So now it is again mapped with the present technology, that is fuel cell electric vehicles and the petrol, hybrid petrol, and the your battery electric vehicles. So you can see for the fuel cell electric vehicles, so the amount is reduced. You can see the earlier graph, that is it was around 7 to 9 euros per kg. Here it is almost it is in the range of 4 to 6 if we adopt the fuel cell electric vehicles. So if it is a petrol, again it is in the range of nearly 9 to I think more than 12 or near to 15. If it is a hybrid petrol, because of the addition of your methane groups, again the cost is reduced using 100% petrol, and instead of that blending the petrol with some methane groups, again that will reduce you the cost, so which is in the range of 6 to 9 plus or minus. And if it is a battery powered electric vehicle, again it is in the range of 3 to 6 nearly. So this is the comparison of comparison cost of fuels. So whatever the conventional fuel we have, electricity we have, and the whatever the hydrogen, and as well as in the form of the fuel cell electric vehicles. So now again this is the ownership cost. You can find some 3 lines, dotted line, that is fuel cell vehicles. What was there in the 2010, that was like costing 9.5 euros per kg of hydrogen, and in 2020 you can see the below line, light color straight line, that is fuel cell electric vehicles in 2020 onwards, the 9.5 it has dropped down to 7 euros per kg of hydrogen. So as we have, there is an advancement in the technology. So 9 cost, that is 9.5 euros to 7.7 it has reduced. And then next one, petrol. So the normal petrol is costing about 1.5 euros per liter. The blended petrol, that is the hybrid petrol, is costing nowadays around 2.5 euros per liter. So in the similar way, ownership cost of your fuel cell electric vehicles and battery electric vehicles. You can see the fuel cell electric vehicles. So in the year 2010, again it was 9.5 euros per kg of hydrogen, and 2020 onwards it has reduced to 7 euros per kg of hydrogen. And if you see the battery electric vehicles, right? So that is 35 octane per kilowatt hour, and if again it is reduced to 20, right? 20 kilowatt per hour. So now, so in the worldwide, how it is mapped, that is hydrogen infrastructure activities. So how the worldwide it is the map wise, right? So you can see in the maps, that is different countries it has been mapped. USA, global, again India also it is mapped. China, right? Korea and other countries are also mapped with the hydrogen infrastructure developing activities. So now coming to the components of a hydrogen refueling station. As I said, present we have the petrol pumps or whatever the petrol or the diesel refilling centers we have either in the highways or in the local areas. So in the present era, we have even the in all the different locations we have the battery vehicle charging, but electrical vehicle charging stations also. So in future also you'll get the hydrogen refilling centers, right? So in that again we have the two types. One is upstream, wherein the electrolysis is a dominant process, and the second one is that how we can convert that into the refilling station. So the first one, whatever the output of the electrolysis, that is a low pressure storage. Whatever we get after the electrolysis process, that is whatever the hydrogen is separated, that is first stored in the low pressure condition, and then it is compressed to increase its temperature, sorry, the pressure, and the high pressure storage. Once it is compressed, it is stored in the high pressure conditions, and it is pre-cooled. So before the dispensing, it is pre-cooled, and finally it is dispensed to the vehicles. So this is the components involved in an if you want to install any of the hydrogen refilling station. So here you can see supply pathways, decentralized hydrogen production on a retail site. So if you want to have an power that is hydrogen refilling station, so now this is decentralized hydrogen production. Means if you want to have an hydrogen refilling station, you can generate on your own in the same place, and you can disperse the hydrogen on the same place. Means right from production to dispense, it is in a single place. That is decentralized. Centralized means somewhere that hydrogen is generated and that is brought to your station, that is refueling station, that we call it as a centralized. Generation is centralized and then it is dispersed to your station, whereas this is decentralized means right from the generation to the final disbursement of the display to the vehicles, it is in a single place, in a single roof, right? That we call as a decentralized hydrogen production. That is right from the production to dispense, it is on a single site or a single under the single roof. So now what are the levels of hydrogen refilling stations you can claim? So that is nothing but you might have seen, if you see any, if you take any of the brands, if they want to give the franchisee, then the franchisees are also in different cadres, right? So your A grade franchisee, B grade franchisee, C grade franchisee, or whatever the D grade franchisee. So in the similar way, hydrogen refilling stations are categorized depending upon their size. Here you can see the very small, that is XS, small, that is S size, medium M size, and the large L size. So the dispenser capacity for a small and the very small is 1, medium is 2, and the large is 4. You can see the difference, that is a maximum throw output per day. So for the very small, it is 80 kg, it can disperse, small can disperse up to 212 kgs, medium up to 420, and the large up to 1000 kgs. So again, the maximum number of refillings per day, 20, 38, 75, and 180. So as your size of the station is increasing, the values are increasing, and the maximum number of fuel cell vehicles, electric vehicles supplied per station, that is right from 100 to 400, 400 to 800, 800 to 1600, right? So this is depending upon what size of the hydrogen refilling stations you want to take. Depending on that, your capacity and the station capacity is also increasing. So now again coming to the specific well-to-wheel passenger car greenhouse gas emissions, that is in the real world driving conditions. So one of the example is taken from the Europe. So here you can find that there are four segments: petrol hybrid, battery electric vehicles, and the fuel cell electric vehicles. And on the other side, we have the grams of carbon dioxide emission per kilometer. So how much gram of carbon dioxide is being liberated per kilometer of vehicle travel. So in 2020, you can see as we are passing on to 2050, the whatever the tank to wheel, right, that has been you can find it, and well to tank also. So well in the sense, right from its how we generate the petrol or the diesel, it is from the purification from the whatever the petrol wells, from first digging from the petrol well, and then again that refining the crude oil, and from the crude oil whatever we have to segregate the petrol and the diesel, right. So from that to the, it is given as a wheels, well to wheels, right. So again in the petrol hybrid, it is quite reduced, because in the hybrid petrol we are blending the methane groups. So that is nothing but the biopetrols. So again in the battery electric vehicles, so you can see the values in 2020 to the 2050. So future it is going to drastically reduce. And again in the fuel cell electric vehicles, again from right from today, in the next 2030 to 2040, the predicted up to 2050, that graph is in the declining form or the decreasing form. So the carbon dioxide emission will be totally brought down to nearly to zero if we adopt the fuel cell electric vehicles. Once again I repeat, if we adopt the fuel cell electric vehicles, so we can bring down the footprint of carbon dioxide to the environment, which will reduce the greenhouse gas emission, and that is the motto of the world which is working on the hydrogen generation. So again you can see the number of fuel cell electric vehicles in the market. That is globally number of vehicles approximately 1 billion today. It will reach up to 2 billions in the year 2050. Correct. So that we can see Japan is leading the race. The next one Europe, and the whatever the USA. You can see on x-axis years, and on the y-axis millions of vehicles. That is maximum 120 millions. Right. So Japan is leading the race. The next Europe and the USA. Then the same trend, if it is mapped with the new registration of fuel cell electric vehicles in the market, so that is on the x-axis you have the years right from 2025 to predicted up to 2050, and on the y-axis you have the millions of vehicles, maximum mapped up to 10 millions of vehicles. So now in this also the trend is same. Japan is leading the race, then Europe and the USA. Then coming to the annual hydrogen demand for fuel cell electric vehicles. So how much demand we have and how much demand is predicted in the future years. That is global hydrogen production today. It is like 45 to 50 million tons is required, right? So again in the x-axis we have the years, on the y-axis we have the 7 million tons maximum hydrogen per annum, right? So here the multiple countries are mapped: Japan, Europe, and the USA, right? So that the trend you can see. So as the years are increasing, the number of vehicles will increase, and again the consumption of the hydrogen will also increase. That is the trend shown in this graph. Then next one, well-to-wheel CGS saving of fuel cell electric vehicles compared to petrol vehicles, right? So that is the trend is shown on y-axis, the years on the x-axis, that is years, and the y-axis, that is a million tons of carbon dioxide, right? So again, that is how much amount of carbon dioxide is being generated right from the refining to the when it is brought to the consumers on the wheel, right? So again, the trend is you can see again the same countries have been chosen, right? So now, what are the policies that ask for the hydrogen economy? So first one is a production process, which includes the cost, efficiency, and the flexibility. The next one, fuel cells. Again, what is the cost, efficiency, and the stability? So in the production process, how much cost it has involved, how efficiency is that process, and how flexible the process is for the generation of hydrogen energy. So in the fuel cells, so how we can generate, or what is the incurred cost while for the fuel cells, and what is the efficiency of the fuel cells, and what is the stability of the fuel cells. So till today also we don't know that whatever the many of the people are using the battery vehicles, battery powered vehicles. So we don't know the life of a battery, whether it will come for 5 years, 10 years, 15 years, right? So again, here also for the fuel cells, the stability is an unmapped area. Okay. Then long-term mass storage, R&D in the materials-based storage. Like so, similarly, this is an challenge again. Long-term mass storage and the R&D in material-based storage. So, what material has to be used in the storage, right? So that it will not give any accidents. Right. The next one, support launch for BUP and micro CHP systems and the fuel cell vehicles. So how we can support that system. Then build up of hydrogen supply and the distribution infrastructure. So as we have discussed, we can either go for the centralized production of hydrogen, or else we can go for the decentralized generation of uh, hydrogen. Okay, central. If it is centralized, you are manufacturing at one place and it is transported to your individual refilling centers. Right. Again, the transportation cost is whatever that we have to bear it. So if it is a decentralized station, you are generating in the same place and you are dispersing to the vehicles in the same place. So that is a added advantage. Your transportation cost is saved. The next one, level playing field plus the sector coupling. Right. What level the market is required, and what all the sectors you can couple with. It is not only for transportation. There are n number of sectors wherein the hydrogen coupling is required. So we already discussed the chemical industries, transportation industry. There are n number of sectors wherein the hydrogen generated can be coupled up for multiple applications. The next one, create or ensure the consumer acceptance. So now if you see, still the people are hesitating to purchase electrical vehicles. If you see the market trend, so even though central government is providing some subsidies for purchasing the electrical vehicle, whether it is passenger vehicle or the goods vehicle. So there are some subsidies from the government. So but still people hesitate to purchase such kind of the vehicles, because still their confidence level is not so high, because they don't know the feasibility of using a battery. Correct. If you take a simple example of your mobile battery, so maximum if you use the mobile battery, it is getting drained after 2 to 3 years. Then after that again you have to replace the battery. So a small battery, if you are replacing after 1 or 2 years, then just imagine a high powered battery which is driving the vehicle. So maximum how much years it can come. So that confidence is not there in the consumers, so that they are not accepting that technology. So in the similar way, still the hydrogen fuel cell vehicles are in the R&D stage. That is why the people are not accepting this technology directly, right? So these are some challenges or the policies to be required in the hydrogen economy. right? Okay, so again, there are again we have discussed in this. We have also discussed the whatever that how to build the infrastructure. I have discussed that is infrastructure can be built in two ways. That is centralized and the decentralized ways. That is the related to the infrastructure. So again, I have discussed as we have the petrol pumps, right? So that are replaced or parallelly we have the electric recharging stations. Again, in future, your hydrogen refilling stations will also come into picture, right? So that is all about the how to build the infrastructure, whether it is in India or whether it is abroad. That is all about the infrastructure, how we can develop. So again, coming to the challenges, again as I have discussed, storing is the biggest challenge, right? Storing the hydrogen, so that is one of the biggest challenge, right? So that is all about I can convey for the today's session. So if any questions are there, the platform is open.
If any questions, please
Sir.
ask. Hello.
Yes, sir. Yes. Good afternoon, sir.
Yes, sir.
Dr. Padmakumar has explained the topic very nicely. I appreciate his collection and knowledge as well. But I have still doubt because I am the my hobby is to research on the new and challenging topics. So my question to Dr. Padmakumar ji is to we have discussed since last 3 days this topic, and we come to know, or even before that also we have the knowledge that as far as the hydrogen gas is concerned, its production, storage, and as well as carrying uh, mm, it's concerned, it is very costlier. And
Yes, sir.
even if it is very costlier, and mm, and we see that in mm, modern countries like Japan, Europe, and USA, they are taking the full benefit of this particular energy, and they are going in right track, and they are utilizing this hydrogen energy or producing the this energy in comfortable way. But in India, though it is that means uh, one of the good future fuel in India, why we are not able to produce it in say in required quantity, or at least in sufficient quantity, so that we can initialize, because as far as our government is concerned, they are very positive about it as far as this production of hydrogen gas is concerned. But in India, we are still very lagging. I think if I have gone through your all the graphical analysis, so in that I never found India in your analysis. So meaning is that we are very lagging in producing this hydrogen gas. So my question to you, Dr. Padmakumar, is that, so what the initiative we have to take, or what the initiative our researchers or our government should have to take, so that this thing we should adopt, and we should produce this hydrogen gas in sufficient quantity, because we come to know that these traditional gases are there are a number of issues with that. So if we are we are in a condition to produce hydrogen gas, then number of problems will be solved. So in that sense, I just want to ask Dr. Padmakumar, what is that issue?
Okay, sir. Yeah, it was a good question. See, sir, as I said, the India is just in the research and development section in the as
Yes,
concerned with the hydrogen generation. Okay, but if you take the even the electrical vehicles, India is has not reached the pioneer stage in battery powered vehicles. Battery, but still we are importing from the China itself. Right, not only India, entire world is importing the battery from the China. Till today, India is not having a sophisticated uh, factory to manufacture the electrical batteries. In a similar way, so you might have seen post COVID, whatever the trend of electrical vehicles has been shooted up like anything. On the grounds, also on the roads, also you can find so many electrical two wheelers, electrical four wheelers, electrical. Nowadays, you can even find whatever the heavy vehicles also. So if you see the locomotive sector, it is drastically changed right from your diesel to your electrification in on the areas, right? In the railway ministry, you might have seen, right? That is using the electricity. So again, that is the reason India is also not sufficiently producing the electricity. Why? Because if everyone starts using the electrical vehicles, it is the biggest challenge to supply the electricity. That is why central government parallelly what they started, Har Ghar, whatever that Surya Graha Yojana. So everyone, every house should have their own electric panels to
solar.
generate the sufficient amount of electricity. So that is the one step wherein the government has taken the initiative to so that entire domestic and your industry people should not depend upon the how we are generating the electricity from your hydroelectric power plant, thermal power plant, and the nuclear power plant. So in the similar way, one of the green way is to just you have to use the renewable energy, that is your solar or the windmills, so that you are matching the whatever the consumption by future, whatever the coming years, right? So that is one, that is with the battery. One example I gave. So when you come into the hydrogen thing, still India is in the research and development stage. So only one output what we have got is that Indian locomotive has launched its sophisticated one of the locomotive, one sample locomotive or the prototype locomotive. So as India will start its or when that locomotive starts its journey, then they will go get to know the what are the real time problems while running a locomotive with the hydrogen, whatever the uh, fuel. But whereas I have mentioned once again, one more example, that is already the Toyota has implemented full-fledged car which is powered by the your hydrogen fuel cells. So that is what India is also tie up with multiple countries for the transfer of technology. So if you see the industries, India is not like as we why do we say India is not a developed country? Is why it is a still developing country? That is one of the what we say very drawback, that India is not focusing on developing the technology. It is a bad truth also, right? India is not nowadays in the last 5 years or 10 years, you can see India is boosting upon, or the central government is boosting upon making our own technology, so that we should not be dependent on any other country. So that will not happen in a over a period of time, that will not happen overnight. So it takes a lot of time and the efforts. That is why first in India or the central government, what initiative they have taken, first let us tie up with the companies which are pioneer in this generation, right? Or the fields which are pioneer in the generation of hydrogen fuel cells. So likewise, India has tie up with so many countries and so many companies to bring about their technology to India. So what is that actually? Their technology they will share with us, and we can produce in within India itself. That is transfer of technology, and later we can parallelly what we can do, we can make a similar kind of the technology which is feasible for India and the Indian roads. So that is that happens over a period of time. It may take another 5 years or 10 years. So wherein just we are now taking the transfer of technology, means for other countries technology we are working on India. We don't have our own full-fledged technology. So that is why again it is difficult to have a full-fledged hydrogen generation stations. In that, again, I have told there are two types, centralized as well as decentralized. So right now the India may work on the centralized platform, because it is also again one of the very risky factor to store the hydrogen. So that is why right now what I think, India will start with the centralized, and later once India gets the full-fledged technology to produce as well as to transport, then we may shift to the decentralized stations for the hydrogen. So that is one more thing. So that is where the India is lacking, and you can nowhere find the India name in any of the analysis or the Indian the map also. So these are the some challenges what the India is facing to build the infrastructure as well as the to feed the futures in the field of our hydrogen energy generation, that is in the form of fuel cells.
Okay, sir. Thank you for your explanation. I want to ask one more question to you in that sense. I hope your specialization is in the same field, so that's why I'm asking. We are, as per as our traditional gases or traditional natural gases are concerned, uh, we are trying for solar, then hydrogen, and what you can say as uh, windmill also. So in that sense, I want to ask you that we are already our government has take initiative in solar. Okay, so now we are though we are not that much of output we are getting, but in lot of state private companies are now also now generating the solar energy from the solar panels. So I want to ask you that solar is now one of the we are taking the good initiative in solar energy. Now, as per as this hydrogen and windmill energy is concerned, I want to compare this. That means which is more efficient, and as per as our country is concerned, which source you want to suggest, or on which we have to work more.
Yeah, good question, sir. So you might have seen my earlier slides wherein for the generation of hydrogen also we are using the three methods. One is gray, blue, and the green. Something we have to burn in the gray and as well as in the blue also. So whether it is fossil fuels or biofuels, correct, sir? So it is
Yes.
liberating lot of carbon dioxide, which is hampering our nature as well as the greenhouse gas effect. So now, what we have discussed in the green energy, sir, we are using the electricity. So that too, which is generated from the renewable sources. That is very important. So in that, India is focusing on the more on the solar energy, sir. So that is why we
Yes.
can find there are more subsidies for the solar energy. But whereas the wind energy, what is the drawback? You cannot install any wind energy or the wind plant on you on the top of your house terrace or in your office, or it is maybe in your factories or the industries. So solar panels can be fitted on your rooftop, your office terrace, and your even the industry, whatever the sheds. It is very easy to
Yes.
install, and it is very easy to generate with the maximum amount of energy with the solar and the solar panels. So that is why
Yes.
India is more concentrating on the generation of
Solar.
electricity by solar. Again, we are using that generated electricity maybe for domestic, maybe for industries, or it may some of the part may go for the generation of hydrogen. So end of the day, we are for a hydrogen generation also, end of the day we are using electricity. But how that electricity is generated, it should be generated from the renewable sources of energy. Then only the motto of green energy will satisfy. Otherwise, it will not satisfy. If you are taking the electricity which is generated from thermal power plant, or if it is generated from nuclear power plant, or if it is generated from hydroelectric power plant, then we cannot call it as a green energy.
Green energy. Okay, sir. Thank you.
Yes.
Any questions are there? Or we can conclude today's session. Okay. I sincerely thanks to our respected speaker, Dr. Padmakumar Bajakke sir, for the insightful session on hydrogen infrastructure and development challenges. Your valuable thoughts on the opportunities, barriers, and the future scope of hydrogen energy have truly enriched our understanding, sir. So, thank you so much for sharing the knowledge. And with this, today we conclude this session. Thank you so much, sir.
Yes, sir. I once again thank the institute and the department for taking this initiative to conduct the FDP and giving me a chance or the opportunity to be a part of this session as a resource person. So I thank sir and the entire team who has organized this FDP for enriching their knowledge. So again, anything you want in the future, like anything you want to go ahead with in the research and developmental activities, my platform is always welcome. So for any kind of the
Yes, sir.
research
Yes, sir.
activities, you can just
Definitely, sir.
contact through sir. You can collect my number from sir also. So anytime you can ping me. Anytime you can just mail me. So whenever I read it, I'll surely reply for that.
Yes, sir. Thank you so much.
Yes.
Yes.